Okay, can you see the screen?
Yes, sir.
Okay, let's hope that it works this time. Okay, are there questions?
Sir, I had one.
Okay.
So we have to renormalize even the free theory, right?
Well, free theory, you don't really need to renormalize that much, except the vacuum energy, right, which you saw has divergence, because masses, etc., don't get renormalized, right, in the free theory.
Okay, okay, that is fine. My point was that the mass m that we are writing, we are going to attribute it to the particle, right?
Yes, and in the free theory, right, I mean that's an exact result, right? We have
Yes.
calculated the spectrum, because how will you define the mass? You will define the mass by saying that there is energy and momentum, and they are related by E equal to square root of p square plus m square.
Yes, and P we have already found out that the eigenstates are actually eigenstates of momenta as well.
Exactly, yeah. Right? So in a free theory, we have defined single particle states, right? Those are exact energy eigenstates, and those do satisfy E equal to square root of p square plus m square.
Okay, but then once we add, let's say, lambda 5 to the power 4 perturbation,
Yes.
we define a new quantity called physical mass, which will be some expansion in lambda. Up to order 1, it is the same as m, but
Yes.
some lambda terms we'll have to include.
Yes.
And that we are saying it's the physical mass that we need to observe.
Yes.
Now we'll start attributing the mass of the particle to be that physical mass.
Yes, exactly.
But shouldn't the so-called mass be an intrinsic property which does not change depending upon what we write on the in the Lagrangian?
Not really, no. I mean, you can have different particles, different theories with different masses.
But that is like saying that electron has like free charge as 1.6 into 10 to the minus 19, but when we add a perturbation, its charge is changing or something like that.
Yeah, but the point is that what you measure is the observed charge, right?
Yeah.
You don't measure the parameter that appears in the Lagrangian.
Yeah, so 1.6 into 10 to the minus 19, is it the observed thing or is it the thing that enters the Lagrangian?
No, it is the observed thing.
And the observed thing remains constant, right? Independent of the whatever interaction is.
Well, see, the point of observed thing is observed after you have taken into account all the interactions, right? So it doesn't really make sense to say that it remains constant.
I mean, this perturbation, it's not always there, right? Or is it?
No, it is always there. It's part of the Hamiltonian, right? Or part of the Lagrangian. So your given theory, say the standard model which describes our world, that comes with a specific Lagrangian. And what you observe are the consequences of that Lagrangian.
So it's not an interaction in the sense that we are perturbing externally or...
No, certainly not. It's part of the theory. Right? It's not that we have a freedom of switching on lambda.
Okay. Like lambda is not a cannot be a time dependent sort of parameter.
Not in the elementary particle physics, right? In some systems, right, when you use, for example, in condensed matter system, you can use quantum field theory. Okay? There you have a way of, making lambda time dependent, because there the lambda can depend on external influence. Okay? But if you are thinking of the theory of elementary particles, right, there is a choice of lambda. I mean, it's part of what nature gives you.
So a theory with lambda 5 to the power 4 perturbation and lambda 5 to the power 6 perturbation, let's say, even though both the theories are renormalizable, I'm guessing.
No, they are not. Okay, but it's okay. You go ahead, yeah.
Yeah. Okay, they are not renormalizable.
Lambda 5 to the 6 is not renormalizable, but it doesn't matter probably for your question. Yeah.
Yeah. My question was that those two theories are like categorically different in the sense that they describe different universes in that sense.
Yes. Indeed.
Okay. All right. Okay, this part is fine. And another thing I had was like if we had two scalar fields in a single theory.
Yes.
The exam problem. But if the two particles had same mass m, How
Yes.
would we differentiate the two particles?
Well, there may be other quantum numbers which are different, right?
Okay.
They may have different charge, for example.
Different what?
Charge,
Okay.
right? So,
But yeah, at the level of scalar field theory, we cannot really say anything.
yeah, exactly, right? So in that case, there is a symmetry, right? So you cannot distinguish them, right? But you cannot you can distinguish. Suppose you have a two-particle state, right? In the two-particle state, if you have 2, 1 or 2, 2 or 1, 1 and 1, 2, these are distinct objects, right? You
Yeah.
can convert 1 to 2, but if the particles are not identical.
Yeah. Otherwise, you would have written a single field.
Yeah, exactly. So it's not that so when there is a symmetry, by definition, you cannot distinguish, right? Two states which are related by symmetry transformation has identical properties. But that doesn't mean that you can assign the theory to have only one particle, right? Because if you take two particle states, right, then you have these distinct possibilities, right? The two particles may be one of them being the first particle, second one being the second particle.
Yeah.
That's distinct from both particles being of the first kind.
Yeah.
Yeah. So in general, when there is an exact symmetry, right, you cannot distinguish states which are related by the symmetric transformation.
All right.
Okay. Any other question? Okay, so let me proceed. Okay. So what we have learned so far is to calculate this Green's function, okay, which I defined as the time ordered product, the vacuum expectation of the time ordered product of operators. And we learned how to calculate this in an interacting scalar field theory. And so what we want to do today will be to study how to relate this to quantities that we can measure, which includes masses of particles and scattering cross section. Now, masses of particles, of course, I have already introduced, you are probably familiar with, but we'll make it more explicit later. Scattering cross section is something that we'll be describing in great detail later in these lectures. But let me just say right now that what scattering cross section refers to is the probability of finding a particular outcome when you take a set of particles and collide them. But we'll make it more precise later. So this will be our goal, but what we'll do is to begin by studying some general properties of the spectrum of states in the theory. Okay, and we'll see what exactly one means by general properties. By the way, can you check if I'm recording?
Yes, you are.
Okay, thank you. Okay, so let's recall that we had defined the momentum operator, okay, as the integral of the energy momentum tensor, okay, and we had arrived at this expression for P rho as the conserved quantity that is associated with infinitesimal space-time translation. Okay, so in particular, P rho is related to transforming phi to phi tilde, okay, where phi tilde of x is phi of x plus epsilon. Epsilon is a 4 vector. And you can expand this for infinitesimal transformation as phi x plus epsilon rho del rho phi x. And P rho is the conserved charge corresponding to this symmetry. We also had identified PIs where I runs from 1 to 3 as the spatial components of momenta, and P0 as the Hamiltonian. Okay, in fact, P0 is minus P0, so you should keep this in mind that if you use P with lower 0, which comes naturally from this, okay, which are the conserved charges associated with time translation, okay, that's related to the Hamiltonian by a minus sign. Now we are going to make use of this conserved charge, okay, because our theory has this conserved charge, the lambda phi to the 4 theory that we are using, that we are studying. So let's recall that there is a general relation that we had mentioned, which is that if Q is the conserved quantity associated with some transformation, say phi to phi tilde, okay, and if phi tilde for infinitesimal transformation takes the form phi plus epsilon chi, okay, then the commutator of Q with phi is given by I times chi. This property we had true for a special class of charges, but we had also said that it's true in general. Okay. And we'll proceed with this assumption that this is generally true. Okay. That if we have a infinitesimal transformation, phi tilde equal to phi plus epsilon chi, and if P is the conserved charge corresponding to this transformation, or see, if Q is the conserved charge corresponding to this transformation, then the commutator of Q with phi is given by I times chi. So this in particular will give you that if you take P rho with phi, that should be equal to I times del rho of phi, because P rho is the conserved charge corresponding to this, or corresponding to this transformation. So we have this relation over here. P rho with phi is I times del rho of phi. Now this relation you can also check explicitly, right? We have the expression for P rho, which is here, and we had derived the expression for T mu nu. We have studied how to find the expression for T mu nu in general for phi to the fourth theory. Okay, so you can apply it to this phi to the fourth theory, okay? And you can explicitly check this, that indeed P rho commutator phi is given by I times the derivative of phi. Now what we'll be interested in today is this commutator, okay, the commutator between P mu and P nu, and what we claim is that this commutator actually vanishes, okay, that this is 0. Now of course, since you have the expression for P mu explicitly, we can check this, right? Because P mu is expressed in terms of phi and pi, and we know the commutators between phi's and pi's. Okay, so you can explicitly check that indeed this is true. But what we will do today is to describe a general procedure, and this general procedure in fact works for calculating this commutator for any pair of Noether charges. And often for this, you don't even need to know the expression for the charges. Okay, you can calculate this just based on the symmetry transformation laws, okay, and without knowing what the charges look like in terms of the elementary fields of the theory. Are there questions so far? Okay, so I'll proceed. So let's begin by calculating this commutator. Okay, double commutator. Commutator of P mu with the commutator of P nu with phi x. Now this, we know what it is. Okay, that is I times the derivative of phi. Okay, so we write it here. And now we are going to make use of the fact that P mu, of course, doesn't depend on the space-time coordinates. It doesn't depend on the space coordinates because it already involves an integral. Okay, you see here that P mu involves an integral, okay, over the space coordinates, and it doesn't depend on time because it's conserved. Okay, when you write down the expression, it does depend on time because time is not integrated over. But by the fact that it's conserved, we know that it doesn't depend on time. So you can take this derivative outside this commutator. So you can write this as I times the derivative of P mu commutator phi x. And now this commutator, again, I can write as I times the derivative of phi x. So that gives I square times double derivative of phi. Now here I have written the same expression, okay, but with mu and nu exchanged. Okay, P nu with P mu phi. That's given again by I square times the double derivative of phi, except that the derivatives have been, the order has been exchanged. But of course it doesn't matter because these are ordinary partial derivatives. Now let's consider the Jacobi identity, which is here. Okay, given any three operators A, B, C, we have an identity of this kind: A, B, A commutator with C commutator with C, A plus cyclic permutation of A, B, C is 0. So you have applied this on this combination p nu and phi. Now, using this fact that the commutator is antisymmetric, okay, we can just massage this a little bit. Okay. So the first thing we'll do is that we'll write this on the left hand side. Okay, these two will bring on the right hand side. So this commutator I'll write as minus of this, minus of this. Okay, so that's this line over here. Now we are going to make use of this relation that AB commutator is antisymmetric. So here what I have done is that I have applied this twice. So first I have exchanged p mu and phi here. And then I have exchanged also this p nu with this commutator. Okay, so two exchanges, that makes it plus sign. So there's no change in sign here. Okay. But I get p nu commutator p mu with phi. Here, what I have done is that I have not done anything here, but I have just exchanged this p mu and p nu commutator phi. So that's here. And now we see that we can apply these relations that we had derived earlier. So p mu phi, okay, is I squared times that double derivative of phi. That's what I've written here. And this one is I squared times again double derivative of phi. But as I have already said, because these are partial derivatives commute, okay, these two are the same. So this is just identically 0. So this proves that the commutator of p nu with phi is 0. Are there questions up to this point? Okay. Now, since this is time independent, p mu and p nu are time independent, we can now take a time derivative and conclude that the same relation holds with phi replaced by the derivative of phi, time derivative of phi, okay, which of course is pi. So what we see is that this commutator p nu commutes with phi and pi, and that means that it commutes with every operator in the theory, right? Because all operators in the theory are made from phi's and pi's. So we conclude from here that this p nu commutator must commute with all the operators of the theory. And this means that p nu commutator must be proportional to the identity operator. Okay? Because an operator that commutes with all the operators in the theory must be proportional to the identity operator. And now we have to make a jump. We'll proceed by assuming that this is 0. That whenever some commutator between two conserved charges is proportional to the identity operator, we'll assume that this is 0. Okay. Now, this is not always true. I should just add that there are rare cases where identity operator does appear in the commutator of conserved charges, but we will not encounter those cases in our lectures. So we'll proceed by assuming that the fact that p mu okay, commutes with every operator in the theory means that p mu commutator must be 0 itself. And now notice that earlier we had said that we'll assume that the vacuum is translation invariant. That means p mu on the vacuum is 0. Okay. That we couldn't have done if there is an identity operator sitting on the right hand side, right? Because if p nu annihilates the vacuum, right, then obviously this commutator will also annihilate the vacuum. Okay. But if there's an identity operator sitting on the right hand side, okay, then that doesn't annihilate the vacuum, right? Identity operator on any state gives you back the same state. So the reason that you can that it's a consistent assumption that the vacuum is annihilated by p mu relies on this fact that there is no term proportional to identity operator on the right hand side of this commutator. Are there questions?
Sir?
Yes, go ahead, please.
Sir, P mu and P nu are the two different conserved charge for different particles.
Not different particles, right? These are the two different conserved charges in the theory, right? It's not that we are assigning different conserved charge to different particles, right? Because we don't even have a notion of particles yet. So what p nu measures is the conserved charge of some state. Maybe you can apply p mu on some state, and that tells you what the conserved charge is. But maybe you go ahead with your question.
Okay, sir. Okay.
So it's not that you have two different conserved particles, right? You are not applying it on particle states as yet. Right? All you are saying is that p mu is a conserved charge in the theory, and their commutator vanishes.
Okay, sir.
Any other question?
Sir, this statement that the identity operator does actually appear in some cases, is it in cases of anomalies only?
Well, sometimes one refers to the anomaly because it leads to anomalies in a different theory. Okay? But at least as it stands, these are unrelated. These are not related. These are not necessarily the case that the theory is anomalous, right? Whenever there's a identity operator appears on the other side. Okay? But often there is a relation between this and the anomaly.
All right.
Because this doesn't necessarily mean that this is not a symmetry, right? Even if there's an identity operator that appeared on the right hand side, right? It wouldn't necessarily imply that the symmetry is broken, right? It just says that the p mu doesn't annihilate the vacuum.
Yeah.
Right? Because what is certainly true is that the symmetry cannot be a symmetry of the vacuum. It has to annihilate the vacuum. It cannot annihilate the vacuum anymore if there is some identity operator on the right hand side. So it will not be a symmetry of the Green's functions. But that's not necessarily anomalous, anomaly, right? Because there are other examples where there is no identity operator on the right hand side, and still the symmetry generator doesn't annihilate the vacuum. Okay. But as I said, often, I mean, there is a relation of these two anomalies, okay? But relation is not direct. Any other question?
Okay.
Sir?
Yes, go ahead, please.
So P mu and P nu are conserved charges, so they commute with the Hamiltonian. So if I take P mu, and H in Jacobi identity, then I should get this from there as well.
Yeah, okay. See, in this case, of course, one of these is the Hamiltonian, right? P0 is really minus H. Okay, but I should just say that it's not necessary that if the charge is conserved, okay, it commutes with the Hamiltonian, because the charge may have explicit time dependence. Right? Angular momentum, the Lorentz generators are of that kind. Right? The Lorentz generator, for example, has an x0 sitting in its expression. So even though the charge is conserved, it doesn't commute with the Hamiltonian. But in this case, you are right that this commutes with the Hamiltonian, right? So, I mean, P0 is the Hamiltonian, or minus P0 is the Hamiltonian. But maybe perhaps you are hinting at something else which I didn't get.
No, actually, I was thinking that then how can we get an identity in the right hand side? But that is not the case. There can be a del t in the right hand side.
Because del t of identity is 0, right?
Yeah.
Okay. So now the point is that because we have seen that these commute, right? All the p's commute with each other. We can choose a complete set of orthonormal basis states, okay, which I'll denote by n, which are simultaneous eigenstates of all the p mu's. So we'll write p mu on n as some pn mu on n. Okay, so these are just numbers, and its conjugate relation is n p mu, because p mu's are Hermitian operators. N p mu is pn mu on n. Okay. So what we learned from here is something that we expect from, of course, everyday experience, that the states in the quantum field theory can be characterized by the total momentum that they carry. total energy and total momentum that they carry. This P and mu, in fact, carries information about the total energy and total momentum of the state. Right now, notice that I have not said anything about whether the states are single particle, multi-particle, right? We don't even know a priori whether the states have particle interpretation or not, right? We have not assumed anything about these except just based on the conservation laws. And these general arguments, we conclude that we can characterize the states by their P mu eigenvalues, okay, which I'll call the momentum of the state. Any question? Okay, so let me proceed. Now we can do a similar thing with angular momentum. Okay, so here I'll be brief, but let me just indicate what happens for angular momentum. Okay, and then I'll leave some exercises for you to do. Okay. So let's recall that this combination half omega nu tau j tau nu, okay, this is the conserved quantity associated with infinitesimal Lorentz transformation. Okay. So what is infinitesimal Lorentz transformation? This is the particular Lorentz transformation that we had. Okay. Phi goes to phi tilde, which is phi plus epsilon omega mu tau x tau del mu phi. And this I have just rewritten as by lowering this index and raising this index as epsilon omega nu tau x tau del upper nu phi, where del upper nu phi is just eta nu mu times del mu phi. Okay? This means del phi del x. Okay, derivative of phi with respect to x. Okay, so now you will use the same formula again. Okay, if this is the conserved charge corresponding to this symmetric transformation, then the commutator of this with phi, okay, must be given by I times this change. Okay, I times this omega nu tau x tau del nu phi. Now, what I have done here in this step is to use the fact that omega nu tau is a totally antisymmetric matrix to write this as a manifestly antisymmetric combination. So I have written it as I by 2 omega nu tau times x tau del nu phi minus x nu delta phi. And the reason that I have done this is because we are now going to use the fact that omega nu tau is these are independent antisymmetric matrices. So except for the fact that omega nu tau is minus omega tau nu, there is no other constant on omega. So we can compare the coefficients of omega nu tau on both sides because both sides multiply antisymmetric combination. Right? J tau nu was antisymmetric in tau nu to begin with. And this is manifestly made antisymmetric in tau nu. So we conclude, and half of course cancels. So you conclude from here is that j tau nu with phi x, okay, this commutator is given by I times x tau del nu phi minus x nu delta phi. So is this clear so far? Again, I mean, if you don't like this kind of argument, you can go back and take the expression for j tau nu, which you have written down explicitly, okay, and calculate its commutator with phi. Right? And you can explicitly verify that indeed this is true. Now let's recall the previous relation that we had. P rho with phi is given by I times the derivative of phi with respect to x rho. And you are now going to use Jacobi identity as before. And this is left as an exercise. So earlier we used the Jacobi identity to calculate P mu, right? Remember here? We use the Jacobi identity to calculate P mu commutator. Okay. Now we follow exactly the same procedure. Okay. We combine these two relations and apply Jacobi identity to calculate this commutator, okay, j tau nu with P rho. Okay. And I leave it as an exercise for you to check that this commutator is given by this combination over here. Okay. And again, we have to ignore terms that are proportional to the identity matrix, right? Because what you will get, so basically what you will show is that the commutator of the left hand side with phi is the same as the commutator of the right hand side with phi. But that leaves the possibility that the left hand side and the right hand side differ by something proportional to the identity matrix. Oh, I should have also said that once you have showed that the commutator of left hand side with phi is the same as that of right hand side with phi, you can again take a derivative and show that the same relation holds for del 0 phi, that is pi. And hence the commutator between of this difference with any field in the theory, any operator in the theory is 0. So this is proportional to the identity matrix. And again, we'll ignore terms proportional to the identity matrix in the analysis. So are there any questions? Is this clear statement? Proof, again, as I said, is straightforward. You have to be a little careful because the main difference is that unlike here, right, we got two derivatives that commute, right? In this case, what's going to happen is that some of the derivatives will not commute because in the expression for, in this, for example, right, you see there are explicit x's, right? So when you now take the commutator with p, right, the p with x of course will commute, right? But sometimes you will find that the derivative is on the left hand left of this x, and then the derivative with respect to x will now act on this x tau to give a non-zero result. That's how you'll get this non-zero right hand side. Okay. But please do this exercise as an exercise. It's more or less straightforward, okay, and verify that this is the case. We'll proceed by assuming that this is the case.
Sir.
Yes, go ahead, please.
So when we want to calculate j with pi, we have to take a del 0. So that j also contains some x0 term.
Yes. So you have to be careful about that. Okay. You have to take into account the fact that del 0 with x0 gives you some non-zero result, but eventually you'll find that those things all cancel.
Oh, okay.
Any other question? Maybe I should have said it in a different way. Okay, that j indeed has an explicit x0, x. Okay, but when you apply this here, right? Suppose you say the j tau nu commutator p rho with phi, okay, is this commutator with phi, and now you're taking the derivative on both sides. Okay? The derivative of j, of course, is 0. Right? J is conserved. When you try to calculate the derivative here, right? When you try to explicitly verify that indeed the derivative of j is 0, okay? Then you have to take into account the fact that the x tau, right, could have a non-zero derivative, and that will be necessary to show that the derivative of j is 0. But since derivative of j is 0 because it's conserved, that we know already, right? We don't have to go back to the expression for j, which has an explicit x. Is this point clear?
Okay, yes.
Because the fact that j is conserved, this follows from Noether's theorem, right? Even if it has explicit x's.
Yes.
Okay. Any other question? Okay, so we can repeat the same analysis for this commutator also, right? JJ commutator. Okay, and you will get some result. Okay, here I have not written down the result, but you can again find out what the result is. Okay, so this one I have already said, right? P nu commutator is 0. Okay. So you can choose a complete set of orthonormal basis states n, okay, which are simultaneous eigenstates of all the p mu's, right? So we'll write p mu on n as p n mu on n, and n p mu is equal to p n mu times n. Now we can consider a different basis, okay, which I'll call n prime, which I have defined here. 1 plus a half I epsilon omega nu tau j nu tau times n. Now you notice that this is the unitary operator, okay, infinitesimal, close to identity, of course, because this omega nu tau, of course, are real numbers, right? This is a Hermitian operator, j nu tau, okay, this, and there's an I here, so this is like 1 plus I epsilon times a Hermitian operator. Okay. So that's unitary, right? To order epsilon, it's a unitary operator. 1 plus I epsilon times a Hermitian operator is a unitary operator. Okay. So this is a unitary transformation from n to another basis, which I'll call n prime. So now, because it's, as I already said, it's Hermitian, we can show that in this new basis, the norm is preserved, right? The inner product, Mn, is the same as the inner product of M prime N prime. Because when you take the conjugate, M prime, right, this plus will become minus sign. And in this product, it will just cancel. Okay. Is this clear to everybody? Any question here? That this is the Hermitian operator and hence the norm is preserved? Okay. So I assume there is no question. Okay. So now I'll leave it as an exercise to show that P mu on N prime. How, okay, P mu on N prime. Okay, so how will you calculate this? The way you will calculate this is that we will use this expression for N prime here. And then we'll use the commutator between P mu and J nu tau, right? Because P nu on J nu tau N, right? We know this commutator. Okay. So we'll rewrite this as J nu tau times P mu on N plus the commutator. Now P mu on N, of course, you know, is Pn mu on N. And P mu J nu tau commutator, okay, will again be a linear combination of the P mu's. Okay, that's, you can see from here. It's a linear combination of the P mu's. Okay. So that again is will give you back Pn mu. Okay. So I'll leave it as an exercise to show that if you take P mu on N prime, okay, that's given by Pn prime mu on N prime plus terms of order epsilon square, where Pn prime mu, okay, this quantity is defined here. Is this statement clear to everybody? Okay, how to prove it? Okay, this is again a simple exercise, but at least what it means should be clear to everybody. Are there questions? Okay, so what it means physically is that this basis N prime, right? Suppose N carries momentum Pn mu. Okay. Then this N prime, okay, carries momentum Pn prime mu. Okay, it's an eigenstate of P mu, okay, but with a different moment, with different eigenvalue, which is P prime N. Okay. And furthermore, from this relation, P prime N mu is given by this. Right? This is just a Lorentz transformation, infinitesimal Lorentz transformation. Right? So P prime N is nothing but the Lorentz transform of Pn by this matrix. Okay. So what we learn from here, okay, again something which is intuitively should be obvious, okay, that by applying this infinitesimal transformation, okay, which is close to identity, by applying this infinitesimal operator, or an operator that is close to identity, that is infinitesimally close to identity, by applying this operator on N, we create a new state N prime, which is still a momentum eigenstate, but with a new momentum, new eigenvalue, and that new eigenvalue is related to the old eigenvalue by Lorentz transformation. Now this I have explained for infinitesimal Lorentz transformation, but of course, as you have learned earlier, okay, that once you have established a relation for infinitesimal transformation, we can build the result for finite transformation by repeated application of the infinitesimal transformation. Okay. And the important point here is that because the error is of order epsilon square here, right? If you do it in n steps, okay, suppose you go build a finite transformation in n steps, okay, then the total error that you will make will be n times epsilon square. Okay. And n times epsilon, of course, is fixed because that's the number of, if epsilon is the step size, right, then you need 1 over epsilon steps to make a finite transformation. So n goes as 1 over epsilon, but n times epsilon square will still remain small, and in the epsilon goes to 0 limit, that can be made 0. So once you have an infinite relation of this kind, we also know that by applying this matrix, applying operators of this kind, infinite number of times, you can actually generate finite Lorentz transformation, and this relation still holds. So what this is showing us is that we can apply these operators of this kind, or the finite version of operators of this kind, to construct a state that carries any momentum that is related to the original momentum Pn by Lorentz transformation. Is this clear to everybody? Are there questions? So we'll proceed by assuming that this is the case, that we can find some operator that relate a state n to a different state n prime, and this n prime, the momentum that the n prime carries, is related to the momentum that n carries by a Lorentz transformation. Okay, so far we have been completely general. We have not said anything about what kind of state we are considering, right? Those states n, right, whether they have particle interpretation also we haven't said anything about. All we have seen is that those states can be characterized by their momentum eigenvalues, and then that given a state carrying particular momentum, we can generate other states carrying other momentum related by Lorentz transformation by applying these operators that I introduced here. Okay, this is the infinitesimal version of the operator, but by applying it many times, you can generate finite version of this operator. Now we'll consider, we'll suppose that the theory has particle of mass mp, and see what its consequences will be. So our strategy will be the following, right? Because see, suppose our goal is to try to find a technique, okay, or find a procedure for calculating these mp. So what we'll say is that let's suppose that the theory has particle of mass mp, and we'll see what its effect will be on the Green's functions that we know how to calculate. And then we'll reverse that procedure to find what mp is. Right? So that will be the general strategy that we'll be following to calculate mp in a given theory. Now let's examine the meaning of this, right? What do you mean by, let us suppose that the theory has particle of mass mp, right? We don't know what particles are. So what do you mean precisely by this statement, that the theory has particle of mass mp? Is that the theory has a class of states for which the energy P naught is fixed in terms of the momentum P by a relation of this kind. If this is true in a given theory, we'll say that the theory has particle of mass mp. And we'll denote these states, which we'll call the single particle states, by their momentum eigenvalue, okay, P, because once the momentum is fixed, the energy is fixed for these class of states.
So would you repeat your statement?
Pardon?
Would you repeat your statement, what you just said?
I am not being able to hear you very well. Can you say it again? I think.
Could you repeat your statement?
Read my statement.
He wants you to repeat your statement.
Okay. Yeah, sorry. The statement that I made is the following. Okay. That we don't know what we don't know a priori, right? What you mean by particles. Okay. So here I am defining what you mean by particles. Okay. That we'll say that theory has particle of mass mp. Okay. If it has a class of states, okay, which are characterized by a single momentum p, okay, simple continuous variable, or a set of three continuous variables, p1, p2, p3. Okay. These level the momentum eigenvalues of this state, okay, and those states should have the property that if the momentum eigenvalues are fixed, okay, then their energy eigenvalue is automatically fixed, okay, and the relationship between the energy and momentum should take this form. Okay. And for some constant mp. Okay. And if we find states of this kind in a given theory, okay, we'll say that the theory has particle of mass mp. Is this statement clear?
So shouldn't we be able to sort of relax this condition in the sense that not all momenta may be conserved, or
See, momenta are of course always conserved, right? Because you have translation invariance. See, we are not saying that this is true for all the states in the theory, right? The theory may also have two particle states for which individual moments are not conserved, right? We are saying that there will be at least one class of states in the theory for which this is true, right? And those we will call the single particle states, okay? Where in the whole universe there is a single particle.
and theories in which we sort of break translational invariance in one direction.
Yes.
What will we do with that? Like,
well, then we have to do with the other two directions. Okay, we have to think of this as a two-dimensional theory, and single particle states will be defining as the ones which have a two-dimensional energy momentum relation.
yeah, okay.
So that will be our definition of single particle states.
Hello, sir.
Yes, go ahead, please.
Can there not be multiple classes of states which have a different relation? As in, P0 is related to P square in for different masses.
Yes, so in that case, there may be multiple single particle states. There may be different kinds of particles, which is certainly possible, right? So there will be one class of states for which a relation of this kind holds, right? There will be another class of states for which a relation of a kind where it is P square plus MP prime square holds, and so on, right? In which case we will say the theory has particles of mass MP, particles of mass MP prime.
But those states would be related by a single kind of field. Let's say we are doing this for phi-4 theory. So we
Yes.
have only one kind of phi. There's no other field.
Yes.
So although there's one phi, but we have different particles of different masses.
We could have in principle,
Okay.
right? For example, there could have been a bound state of two phis, right? Two particles.
Yeah.
Because they're interacting
Okay.
theories, right?
Yeah.
That could be a bound set of two particles, right? Which will also give rise a relation of this kind. But MP will now be the mass of the bound state.
Yeah. Okay.
Right? So that certainly things like that could happen. Any other question? Okay. So now we can apply our previous discussion on this state. Okay. So we define the state P prime, right? What is P prime? Okay, this is the result of acting with this operator on that state. So you know that state carries, that state is a momentum eigenstate, and the momentum eigenvalue is given by some P prime. How is P prime related to the original P? It's related by a Lorentz transformation of this kind, right? EP prime P prime is lambda times EPP, because that's what we had established, right? That this is also a momentum eigenstate, and which is and the momentum eigenvalue is given by the original momentum eigenvalue, okay, after Lorentz transformation. Now, given this, okay, so notice the proportionality constant, right? Because whatever we have discussed earlier, okay, here at this level, okay, shows the eigenvalues. Okay, the eigenvalues are equal. Not the eigenvalues are equal, but eigenvalues are related by Lorentz transformation. But we would like to normalize the state such that this holds as an exact relation. That when we apply, so this means that we start with the state P and apply that operator, the unitary operator. We would like to define the normalization of the states in such a way that this is exactly the momentum eigenstate of the same single particle state, okay, with a new momentum P prime. But this relation, okay, as we will now see, is in conflict with the usual way normalized particle states. So suppose we have normalized it this way. Then it follows that if we take the inner product between this P1 prime and P2 prime, okay, the transformed states, this is equal to P1, P2, right? This follows from this. This follows from this relation, okay? And that in turn follows from the fact that this is a unitary operator. Okay, this is Hermitian. Okay. So there are many primes in many places. You have to be a little careful in following the place where the prime is. Okay. So this is given by P1, P2. Now, on the other hand, if we assume that the normalization here, right, there is a relative normalization, that this is the same as the original momentum eigenstates, okay, with momentum level replaced by P prime, then you know that this also has to be equal to this. So you conclude, so what is the conclusion? That the inner product between P1 and P2 should be the same as inner product between P1 prime P2 prime, okay, where P1 prime is a Lorentz transform of P1 and P2 prime is a Lorentz transform of P2. But now we see that if we use the conventional normalization of these states, P1, P2 proportional to delta Q, P1 minus P2, then that's incompatible with this relation. And the reason that this is incompatible with this relation is that delta Q, P1 minus P2 is not the same as delta Q, P1 prime minus P2 prime. So let me explain why this is not the case. Now it's clear that if P1 is P2, right, if you set P1 equal to P2, then P1 prime is the same as P2 prime. Right? That follows from this relation. Right? If the so there is delta Q, because both are transformed by the same Lorentz transformation. Right? P1 will be transformed by this Lorentz transformation, P2 will be transformed by this Lorentz transformation. Okay? But the problem is in the normalization. Okay? So the problem is here. Okay? So you look at this relation between P prime and P. Okay? In order that this relation holds, we have to make sure that the Jacobian, right, the determinant that you get of the 3 by 3, the lower 3 by 3 block, right, because P prime and P are related by this lower 3 by 3 block, right, that you have to make sure the determinant that you get in this lower 3 by 3 block, that has determinant 1. But that's of course not the case for Lorentz transformation, right? The Lorentz matrix lambda has determinant 1, okay, but as a 4 by 4 matrix. If you just pick the 3 by 3 matrix, okay, that acts on the space coordinates, that has no reason to have determinant 1. And indeed, in general, it doesn't have determinant 1, okay, except for the rotation generator, right, which of course acts only on the lower 3 by 3 block. Okay. In general, for a general Lorentz transformation, okay, the lower 3 by 3 block, okay, doesn't have determinant 1. Okay. And because of this, we know that this relation is not true. Is this clear? Okay. So the conclusion is, okay, that if we want to normalize the states such that this holds, then we cannot also choose that this relation holds. Okay, because this combination is not Lorentz invariant. Fortunately, there is a remedy, okay, and the remedy follows from the following claim, okay, which I'm going to prove in the next slide, okay, that while this is not Lorentz invariant, okay, if you take the combination 2 EP1 delta Q P1 minus P2, okay, this is indeed the same as 2 EP1 prime times delta Q P1 prime minus P2 prime. Okay, because EP1 is also not equal to EP1 prime, but the change, the Jacobian that you pick up in relating these two, okay, exactly gets compensated by the relationship between EP1 and EP1 prime. Okay. So this combination is indeed Lorentz invariant. Okay. So that suggests that we should normalize the basis states for single particles of mass MP such that P1 P2 inner product is given by 2 EP1 times delta Q P1 minus P2. Are there questions on this?
Sir, instead of defining our states by 3 momenta, could we define our states by 4 momenta and then use delta for P1 minus P2 equal to?
Yeah, see the problem is that for single particle states, right, the fourth component of the momentum, the P0, is already determined, right?
Yes.
So suppose you use delta 4 P1 minus P2, right? Then you will get a factor of delta of P0 minus P0 prime.
Yes.
But the problem there is the delta of P0 minus P0 prime, because you already have del P equal to P prime, right? Delta cube of P minus P prime. Okay? That sets P0 equal to P0 prime already, right? Using this relation. So you'll get delta of 0, right? Which is an infinite quantity. So if the state had been characterized by 4 momentum, 4 independent momenta, then what you are saying is correct, and that would have been a perfectly good way to normalize the states. But because for single particle states, the states are leveled by 3 momenta, right? The fourth one is automatically fixed. Right? There, delta 4 P minus P prime or delta 4 P1 minus P2 would have given infinite normalization, right? Because there will be an extra delta of 0.
Sir, but this happens in usual quantum mechanics also, right? Where P prime is delta P minus P prime. That is also for P equal to P prime, that is also infinite.
No, for P equal to P prime, that's infinite, right? But here for all P prime, it will be infinite.
Oh, okay, okay.
Right? Because if you take delta P, delta X times delta X, right? That's not a well-defined quantity, right? Delta X is well-defined, right? But delta X times delta X is not well-defined, right? I mean, that's what will happen here, right? Because already delta cube P minus P prime, right, sets P equal to P prime. So anything that multiplies it, you can set P equal to P prime already. But that in turn will set P0 equal to P0 prime, right? Because P0 is given by this, and P0 prime will be given by the corresponding thing with P replaced by P prime.
Oh, okay, okay. So this problem will not happen in multi-particle state.
No, if you want to normalize it, that a multi-particle state, this problem will not happen, right? But there may be other reason why you don't want to normalize multi-particle states this way. But at least this problem stated as stated will not happen for multi-particle states.
Okay.
Other questions? Okay, so this relation, okay, you can verify explicitly, right? Because given a Lorentz transformation, you know what the Jacobian will be for the 3 by 3 block, right? And you also know the relation between EP prime and EP, okay? And you can explicitly check that indeed the Jacobian that you pick up, the Jacobian you will pick up in relating these to this, okay, exactly gets compensated by the corresponding factor that relates EP1 to EP prime 1. And you can, in fact, verify this by infinitesimal Lorentz transformation. Okay, because once you have verified this for infinitesimal Lorentz transformation to order epsilon, this also holds to higher orders. But what we'll do here is to give a different proof of this fact, right, which doesn't require doing explicit calculation, okay, but just manipulating some delta functions. Okay. So here we'll start with an expression of this kind, and I have marked some things by red because most of the manipulation will basically involve the red quantities. Okay, so let's see how you go about manipulating this. So what have we started with? So we have started with the quantity that you want to prove is Lorentz invariant, right, which is not manifestly Lorentz invariant, this one. The rest of the quantities are manifestly Lorentz invariant, right? Delta of minus P1 square minus MP square H P1 0. Right? These basically sets P1 0 equal to square root of P1 square plus M square, MP square. And similarly, this basically sets P2 0 to be square root of P2 square plus MP square. Okay, so these single particle relations, right? These relations are explicitly implemented by delta functions. Okay, but I've chosen to implement it in the form in which these are manifestly Lorentz invariant quantities. So first to second line is really nothing. I have just written minus p1 square, okay, as p1 0 square minus p1 vector square, okay, by using this definition. Okay, everything else is unchanged. So now next step, okay, I have manipulated here. Okay. See this delta function, right? What it does, it sets p1 0 to be equal to plus minus square root of p1 square plus mp square, right? That is plus minus ep1. But because of this heaviside function, the step function, only the plus sign is relevant, right? The minus sign vanishes, right? H is 0 for p1 0 equal to minus ep1. So basically then this combination can be rewritten as delta of p1 0 minus ep1, except that there is this, because inside the delta function, right, is the p1 0 square, you have to, when you convert this in terms of delta of p1 0, you have to divide it by the derivative, right, which is 2 p1 0, which you can relate by 2 ep1, right, because delta of p1 0 minus ep1. Now that's next step, you see ep1 and ep1 cancels, this 2 ep1 cancels the 2 ep1. So you only have delta of p1 0 minus ep1. But now I claim that this ep1 can be replaced by p2 naught. Okay, so let's see why that is the case. So this is multiplied by delta of p1 minus p2, right? So I can replace p1 by p2 inside this argument. So delta p1 0 minus ep2. This delta function ensures that p2 0 is equal to ep2. So the ep2 I can now replace by p2 0. So using that, I can write this as delta q p1 minus p2, delta of p1 0 minus p2 0. Okay, these two have cancelled, and then these delta functions have left as it is. And now you see that by combining these two, I get delta 4 p1 minus p2, and then this remains as it is. And you notice that this quantity that has appeared on the right hand side is manifestly Lorentz invariant. Delta 4 p1 minus p2 is Lorentz invariant, right? Determinant lambda is of course 1, and this combination is also Lorentz invariant that we have discussed earlier. So what we see here is that we have a relation, right, that relates this to this. Right hand side is manifestly Lorentz invariant. So this means that the left hand side must also be Lorentz invariant. But on the left hand side, this part is Lorentz invariant, this part is Lorentz invariant. So that means that this must be Lorentz invariant. And that's what we wanted to prove. So this combination is Lorentz invariant. Are there questions? Okay. Okay, so given this, from now on, we are going to normalize momentum eigenstates of single particles in this fashion. So instead of taking this to be delta cube of p1 minus p2, we'll take it to be del 2 ep1 times delta cube of p1 minus p2. This will ensure that we can make use of this relation freely. Okay, that we can make use of this relation. Okay, because we are going to make use of this relation freely in what follows. Are there questions? Okay, so let me proceed. So the next thing we want to do is to want to understand the meaning of completeness, right? This relation, right? What it means with this new normalization that you have chosen. Now, of course, if n had taken discrete values, right, then there's no confusion, right? This sum is quite well defined. But what you are asking is what about the continuous momentum levels? Okay, in particular, we have this continuous momentum level, which is a 3 vector for the single particle state of mass mp. Okay? What should it mean for this? Now, in the earlier normalization, right, normally in non-relativistic particle mechanics, the way we normalize the momentum eigenstates, this sum would have meant just this, yeah, or maybe some 2 pi cube factors thrown in, but it would have meant basically this up to a normalization. But with this new normalization that we have chosen, Okay, one can easily convince oneself that this doesn't act as normal as identity on the single particle state. So let's just verify that, right? Let's suppose we have this combination and apply it on the single particle state carrying momentum P1. Then this we can evaluate, okay, because the inner product we have normalized here. So that will give you, so this part will leave as it is, that will give you 2 EP1 times delta cube of P minus P1. And now when you do the P integral, right, you just set P equal to P1 using this. So you get 2 EP1 times P1. Okay, this P gets replaced by P1. And we see that indeed we don't get back P1, right? We applied this on the state P1. So if it was acting as identity operator, we should have gotten back the state P1. Instead, we get back the state 2 EP1 times P1. But this, of course, suggests an remedy, right? What you should do. And the remedy simply is that what will include, okay, what it means, as what we will mean by the sum, okay, when it comes to single particle states, okay, is that we'll write this as integral dq p over 2 ep times this combination pp. In that case, this 2 ep will be replaced by 2 ep1 because of this delta function, and we'll cancel this 2 ep1 that appears here. Okay, and we'll get, so this acts as identity acting on single particle states. Are there questions? Okay, so now we are going to proceed with this. And the final assumption that I'll state is this, that we'll proceed by assuming that the vacuum is Poincare invariant. See, Poincare symmetry means it's a combination of translation and notation and Lorentz transformation. Right? That the vacuum is invariant under all the symmetry generators, which means that it's annihilated by P mu as well as by the angular momentum generators J nu. Okay, and these are the conjugate relations. And again, let me emphasize that this kind of relation, this assumption wouldn't have been possible, okay, if any of these commutators, okay, had terms proportional to the identity on the right hand side. Okay, because then this would be inconsistent, right? To assume that this annihilates a vacuum. Are there questions? Okay. So now we have got all the machinery, okay, and we'll now start analyzing the two-point function. Okay, we'll not be able to finish the analysis today, but we'll hopefully do it tomorrow. So we recall that our definition of the two-point function, that the one that you know how to calculate, is this time-ordered product, vacuum expression of the time-ordered product of operators, which I'll write as the step function. If x1 naught is larger than x2 naught, then it's g plus x1 x2, where g plus x1 x2 is just this. And if x2 naught is larger than x1 naught, then it's g plus x2 x1, right? The order gets reversed. So it will be phi x2 phi x1. Now here, we are going to insert a complete set of states. Okay, so between phi x1 and phi x2, I insert identity. Okay, so I write this as sum over n omega phi x1 n n phi x2 omega. Okay. So our strategy will be that we'll see how single particle states contribute to this. Okay. And then we'll eventually reverse this, okay, to compute MP. Right? Once you understand what is the contribution to G plus X1, X2, okay, from single particle states, okay, we'll translate to the contribution to G X1, X2 from single particle states. Okay. Now G X1, X2 we know how to calculate. Okay. So we'll use that to derive what MP is, right? To find systematically what MP is. Okay. Because the contribution from single particle states, of course, will depend on MP. Okay. But let's now proceed. Okay, let's not do it immediately. Okay, I'm just telling you, giving a preview of what we will eventually do. Okay, but for now, let's proceed by including all states. Okay, we will not assume that we are including only the single particle states here. Okay, we want to be exact as much as possible. We include all states in this sum. Okay, and see what we can say. Now, the first thing we'll do is to analyze the structure, the x dependence of these quantities. Okay, and that fortunately is simple. Okay. So for this, we use the fact that if you take the derivative of omega phi xn, this derivative, of course, can be taken inside because we are using the Heisenberg picture, right? These are all time and space independent. Okay. So you can take the derivative on phi, okay. And then we use the fact that p mu commutator phi is I times the derivative of phi with respect to x mu. Okay. So this we can write as minus I times omega p mu commutator phi sin n. So let's open it up. Okay, write it as p mu phi minus phi p mu. And then let's use the fact that p mu on omega is 0. Okay, and p mu on n is pn mu. Okay, so this can be written as this minus sign cancels this minus sign over here. So I pn mu times omega phi xn. So now if you compare the left hand side and the right hand side, you see that you have a nice differential equation. It's a first order differential equation for this quantity omega phi xn, okay. And it can easily be solved, right, with the initial condition put at x equal to 0. So you get omega phi xn is e to the I pn dot x times omega phi 0 n, and its conjugate relation is n phi x omega is e to the minus I pn dot x times n phi 0 omega. Are there questions? Okay. So now, if you substitute this in the expression for this, right, x1 dependencies have been extracted out. We get g plus x1 x2, okay, is e to the I pn dot x1 minus x2, right? From here you get e to the I pn dot x1 because you have omega phi x1 n, okay? And from here you get e to the minus I pn dot x2. Okay? So you get e to the I pn dot x1 minus x2 times this. Okay? And I'm now going to rewrite this in a slightly different form, okay, which will look trivial at present, okay, but it will be useful later. And the way we'll do it is this, okay, that we'll use the fact that this is just up 1, right? Integral d4q of delta 4 pn minus q is just 1. If you integrate over q, right, there's a single delta function, so you just get q will be set equal to pn and you will get 1. Okay. So you can always multiply this by 1. Okay, that's what we are doing here. We are multiplying this by 1. In the next step, all I'm going to do is that integral d4q I'm going to pull out. That can always be done. But once we have pulled it out, this pn I can replace by q because of this delta 4 pn minus q. Okay, because after you do the q integral, it will be q will be replaced by pn anyway. So I can write this to the iq dot x1 minus x2. But once you have written it this way, this is now not dependent on n, so I can pull it out of the sum. So I have written this integral d4q over 2 pi to the 4 e to the iq dot x1 minus x2 times fq, where fq, okay, this 2 pi to the 4 is just a normalization that I have included. So fq will have a 2 pi to the 4 to cancel this, okay, and then the rest is sum over n delta 4 pn minus q and then this. Is this clear so far? Any question? Okay, so here I have written down those two equations again. Okay, so g plus is given by the integral of fq. So basically it says that fq is a Fourier transform of g plus. Okay. But here you have an explicit expression for fq, which is here. Now one thing you may notice from here, this expression is that g plus depends only on the difference x1 minus x2. Okay. But that's not a surprise. Okay, that's not a surprise because we have the transition invariance, right, which tells us that G plus, this should have been G plus x1, x2 is equal to G plus of x1 plus a, x2 plus a for any 4 vector A. Right? And that's the reason why it depends only on the difference x1 minus x2. Right? Because x2, for example, you can always set equal to 0 by choosing a equal to minus x2. So using this, we can reverse this relation, okay, and write fq as the inverse Fourier transform of G plus. So again, this should have been G plus. I'll correct this. So fq is given by integral d4x e to the minus iq dot x times G plus x0. Right? So all I have done here is that I've set x2 equal to 0. Right? So this becomes e to the iq dot x1 fq, and then I do the inverse Fourier transform to write this as the Fourier transform of G plus x1 0. Okay. Now using this, okay, and this relation over here, so we'll basically we have two expressions for fq. One is this, the other one is as the Fourier transform of G plus. Okay. We'll prove these relations, right? We'll first of all prove that fq is Lorentz invariant. Okay. That means if we replace q by lambda q, then f takes the same value. Okay. And then the second relation that we'll be proving is that fq vanishes for q square positive, okay, which means when q is space-like, and independently also for whenever q0 is less than 0. Okay, this is true irrespective of whether q is space-like or time-like. Okay. So fq will vanish whenever q square is positive, okay, and also whenever q0 is less than 0. So I think this I'll try to, I'll start the discussion tomorrow. Okay. So I'll stop here today. So are there questions?
Hello. So what is the goal here? I mean, what are we trying to do?
See, eventually the goal will be that in this sum, right? I have introduced this in the sum over n.
Yeah.
Yeah. Okay. Let me go back here, right? So the goal. So at this stage, I have been totally general, right? So eventually, the goal will be in the sum over n, right? If we restrict it to the single particle states, that will give certain kind of contribution to fq, which will give certain kind of contribution to G plus and hence to G. Okay, because G is given in terms of G plus. So the point is that we know how to calculate G. So we will try to see that knowing given that we know how to calculate G using Feynman diagrams, okay, or there may be other ways to calculate G. Okay. How to extract MP from there, right? That's the question we asked. Right? So the idea is that we'll see what will be the contribution of single particle states to a sum like this. Okay. It will first study the contribution of single particle states to FQ. Okay. Then from there we will translate it to G plus. Okay. And from there we will translate it to G. Okay. And then we will use the fact that we know how to calculate G to see how to extract MP.
Okay. Yeah. I mean, all these calculations are exact, right?
So far it is exact. So far you have not made any assumption, right? So okay, one of the goals will be to find out some general structure of FQ. That we'll see, but the specific application that we'll be making is that we'll try to find the systematic procedure for calculating MP. Right? That suppose somebody gave you 5 to the 4th theory, right? And said, okay, lambda is small, you can do perturbation expansion in lambda. Okay. Now give me a procedure for calculating MP systematically as a part series expansion in lambda. Okay. And this is what we learn how to do by doing this exercise. Okay. But so far it is completely general. Right? The sum over n includes both single particle states, multi-particle states, everything, right? It's in fact general enough so that even if n didn't have particle interpretation, it is still true. So whatever you have done is still going to be true.
Okay. Yeah.
Are the other questions? Yes, go ahead.
Is QFT like useful only when we have a particle interpretation, or is it otherwise also useful?
No, otherwise also it's useful, right?
That you're saying.
I mean, there is a special class of quantum field theories called conformal field theories, which do not have particle interpretation. But it's still a useful tool there as well.
All right. I think Harshit was asking something.
Yeah, I was asking one more thing. This commutation, the failure of commutativity of P mu and P nu, is it related to some kind of discrete symmetry breaking?
No, it's true also for continuous symmetries.
No, there could be one case in which the discrete symmetries are broken, and that's why this is failing, this commutation relation. There could be multiple things, but I'm asking specifically for discrete symmetry.
See, for discrete symmetry, of course, you don't have generators of this kind, right?
Yeah.
So for discrete symmetries, right, it's not the commutator that is important. I mean, you have to define something else. So the commutator that appears in the case of continuous symmetries.
No, P mu and P nu were defined using some kind of continuous symmetry, but they are the fact that they are not commuting. Is it because some kind of discrete symmetry has been broken?
Not
I mean,
yeah.
Yeah, I'm kind of trying to say this in the way we say it in general quantum mechanics. We say that the two momentum operators commute because whether we move first in x direction and then in y direction or the other way around, it does not matter.
Yes.
And in kind of it is saying that whether we move from one point to other point clockwise or anti-clockwise, it does not matter.
Okay.
So if these two operators are not commuting, then the fact that we are moving clockwise or anti-clockwise is a part of our description.
Yes.
So this clockwise and anti-clockwise are kind of discrete discrete symmetries.
Yeah.
Let's say yeah, that's why I'm saying if some kind of discrete symmetry is broken, that's why this commutators are not valid. Like
okay, yeah. I think
these
what
two operators are not commuting.
Yeah. So what you are saying is related to, would be true if this commutator had not been 0, but it would have been equal to some other symmetry generator. Okay, which could be related to some discrete symmetry, for example, right? But here the identity operator, right, is it commutes with everything. It doesn't generate any symmetry. That's the kind of non-commutator, the lack of commutativity that we are describing here is not that this gives you something, right, which acts non-trivially on certain states. Because that we have already ruled out, right? Because it commutes with everything. So in a sense, this is not a symmetry transformation. What is appearing on the right-hand side is the identity operator, right? It acts in the same way on all states. So it's not that for some states it will give you one value, for another state it will give you another
value. Consider this example. Our theory maybe, let's say it is a reflection invariant in, let's say, x direction.
Okay.
So px and py,
yes,
they should, this commutation relation should be something. And if they do not commute, it should be something proportional to identity.
Okay, yes.
And that something on the right hand side is a C number times identity operator.
Yes, yes.
So if let's say on the left hand side we have this commutator px and py, and we take like now we are doing a sort of reflection kind of operation in x direction.
Okay.
So the px will change to minus px.
Yes.
And the py will remain invariant because that won't be reflected.
Okay.
So we have minus px commutated with py.
Okay.
And on the right hand side, nothing will happen because the operator that we will use to make this sort of reflection is commuting with that identity operator.
Okay.
So in general, if there had been reflection invariance, uh, if we sum these two relations, the commutator of px and py and commutator of minus px and py, this should sum up to 0.
Okay.
But
Yes.
on the right hand side, we have two constants which are non-zero. So
Okay.
that kind of implies that there was no reflection invariance initially.
Yeah, but see, in this case, we could have, for example, in 5 to the 4th theory, right? Reflection invariance.
Yeah, I mean, that kind of can be broken.
Okay, it can be broken, yes.
So that is, I mean, essentially it turns out that some kind of symmetry is breaking. That's why we have this kind of non-commutativity.
Okay, yeah, I'm not completely sure that I follow this chain of logic, but I'll have to think about it, right? Maybe if you can write and send it to me,
Okay, yeah.
the details, I'll try to look at this and see if I can make a more concrete statement.
So I think he's simply saying that if it's actually non-zero, some C times identity, the px py commutator, and you apply the parity operator in x direction while applying the px py commutator on a state. So the parity operator will simply go through identity and act on the state, whereas on the LHS it will give minus px py and then the parity operator acting on the state. If the parity operator actually left the state invariant, then this statement cannot be true. So the parity operator does like change the state to something non-trivial. In the sense that the state is not parity invariant.
Yeah, but the question is, I mean, does that mean that whenever this parity operator is broken, you'll have something non-zero on the right-hand side? I don't think that is true.
I mean, I'm not saying that. If that is broken, I mean, if these two operators do not commute, that must be because this parity operator is not changing. This parity operator is changing things in the theory.
Okay, so you are saying that if the theory had parity invariance, you may be able to rule this out. Is that what you are saying?
We may be, but we are not sure. If this is not commuting, if px and py are not commuting, that is only possible because our parity a parity operator does not act trivially. That's
Yeah.
what I'm saying.
So what I'm saying is that that if parity had acted trivially, right? If parity was a symmetry,
Yeah, then this would not have happened.
It shouldn't have happened. Yeah. So maybe that's a concrete statement that we can try to prove. Okay, so this I'll try to think about. Certainly, it's possible that sometimes, I mean, often it happens that when you have enough symmetries, you can rule this out, right? Rule out the existence of these kinds of operators by using Jacobi. Okay. And in this case, you are adding some discrete symmetries, and it's possible that by combining the existence of the discrete symmetry with the algebra, we can try to rule it out. Okay. In this particular example, I am not completely sure, but I have to check. Right? But in general, that is certainly possible. That if you have enough symmetries, you can often show that the algebra doesn't admit the central terms. Right? So these are typically called central terms because they commute with everything. And certainly there are examples where you can rule out existence of such terms just based on the algebra.
So when you said that sometimes it happens that the commutator is actually non-zero and something proportional to identity, was it for like momentum operators or in general some conserved charges?
No, in general some conserved charges.
Like, do we have like simple, well not simple, but like conventional theories where momentum also does not admit this?
I think just momentum. I think always has no central charge, right? I think that probably one can even prove by using Jacobi identity informing the Lorentz generators. I'll try to think about this. But there, algebra that are close to momentum algebra, right, which are generalization of the Lorentz algebra, which are conformal algebras, which do admit terms like this, the right hand side proportional to identity.
So there the operators might not, like, I'm not sure, but like here the momentum actually act with the parity operator in the sense that px goes to minus px. But in general, an operator may not be even affected by a parity operator or some discrete symmetry.
Yeah, but that's not necessary in those cases. I'm gonna, again, I have to try to look for examples. Okay? Because see, if there are two of them, right, if both of them transform, for example, then there's a problem, right?
Yeah.
Okay? So yeah, that's what I said. It depends on the details of the algebra.
Yeah.
Okay, that sometimes, but just based on the algebra, you can rule out this because it's inconsistent with either Jacobi identity or, you know, for discrete symmetry, some identities of the kind that you are mentioned. And that's certainly possible.
Also, lastly, if Harshit is done, I had one thing regarding renormalization.
Yes.
Outright on the onset of the theory, like you immediately said that 5 to the 6 is not renormalizable.
Yes.
Like one thing I can see is that when we actually write down the expressions in terms of lambda exponent, like lambda, order lambda term, order lambda square term, and all of those, and like write down all the divergences, we are, that is going to infinity, but we are setting it to some MP value, some observable quantity. And then while calculating other observables, we are just replacing those divergences by MP. That I can see. Like, I don't see when we will not be able to do this. Like we'll certainly not be able to do this when there are so many forms of divergences that we do not have enough physical quantities to equate them to.
So that's what happens in this non-normalizable theorem. That's precisely what happens, right? In the 5 to the 6 interaction in 4 dimensions.
Okay.
You basically see that as you go to higher and higher order, right, the more and more quantities start becoming divergent.
Like qualitatively different divergences.
No, same kind of divergence, except that the more different amplitudes start becoming divergent.
All right. Yeah.
Right. I mean, once you include 5 to the 6, right, then the 6-point amplitude, 8-point amplitude, 10-point amplitude, all of these are divergent.
Yeah.
And you don't have just enough. I mean, you need infinite number of quantities to adjust, right? So the theory has infinite number of parameters now.
Okay.
So that's what one means by theories being not renormalizable.
So, like as a prescription, we should only write in the Lagrangian like renormalizable terms, or we should find a new mechanism for dealing with non-renorm.
Well, the standard approach is that you use only renormalizable terms.
Okay.
But as I said, in string theory, for example, everything is finite, so you don't need renormalizability, right? But there, of course, you cannot add anything, right? You have to basically take the theory and do whatever the theory tells you to do.
Okay.
Okay, I think somebody is trying to log in the same account, so I have to log out. So we'll continue tomorrow.